we introduced the prime numbers, and we proved a couple of important things. The fact that there's an infinite number of prime numbers, Euclid's proof, really nice important proof in number theory. And then we also proved the fundamental theorem of arithmetic, which said that every number, every integer factorizes uniquely into primes. So that gives us a canonical representation for a number, which is very kind of useful. Seeing a number in terms, by number I mean integer, seeing an integer in terms of its prime factorization. So when you see an expression like this, this is expressing an integer n as a product of powers of the pi. The pi are each prime numbers. So the p1 up to pr are the r prime factors that happen to be divisors of n, and each of them might divide in a certain number of times into n. So they have an exponent there as well. And the key tool the key result, which really proves the uniqueness part of the fundamental theorem of arithmetic for us, was we gave it the name Euclid's lemma. It appeared as an exercise in the chapter 2. And Euclid's lemma said that if you've got a prime number dividing a product of numbers, this implies that P divides A or P divides B. You could divide both. Remember this logical OR. Mathematical logical OR is inclusive, so P divides A or P divides B means it could divide them both. Whereas, in the outside world. Sorry? It proves that if, so this is the statement, it's an implication statement. If P divides the product, then P must divide A or it must divide B. So it has to divide one of the factors. This is where P is a prime number. It's the key property of prime numbers. See, it's not true of composite numbers. If this is a composite number here, it could divide the product, and you could have part of the composite number in A and the other part of it in B. And that would prevent it from cleanly dividing A or B. But the prime numbers you can't break up. That's what they are.
What do you mean cleanly divided?
Just dividing in the sense of chapter 4, one integer dividing another one. Yeah. Sorry, chapter 2. Being divisible. So this was the key ingredient that went into proving the FTA, which established this canonical form, this unique representation for integers. So, I mean, what humans know about prime numbers is really a mixed bag in a lot of ways. Certain things we know for sure about them. Other things we haven't. There are lots of results that we suspect might be true of the prime numbers, but we don't yet have the proofs of them. We can't yet say that we know this property one way or the other. So, for instance, we've proved already that there's an infinite number of them. Okay. And we can prove that there must be an infinite number of them, but that doesn't mean we can easily list them all. Essentially, there's really no better way of listing all the prime numbers than just testing each integer in turn to see whether it's prime or not. And really, we don't really have a good way of testing whether an integer is prime. That's much better than just trying to divide it by everything smaller than it. And there are some speed ups and some, if you know something about the number you're testing, you can often be a bit better than that. But essentially, the way to test whether an arbitrary number is prime is, not much better than just testing to see if it's divisible by anything. So we know there's an infinite number of prime numbers, but there's no easy way to list them all, apart from just the naive way of testing each number in turn. Okay. So there is, I think we looked at it in our tutorials. We mentioned the Great Internet Mersenne prime search, GIMP's prime search. So there's the largest known prime that we found using computer search. Okay, and every so often we find the next new one. Okay. So that indicates the fact we're using computers and testing loads and loads of numbers we've no easy way to step from the largest known prime to get the next one, apart from just searching and testing for it. So there's that aspect of prime numbers which is elusive, which is not within our grasp. So I would finish off this chapter just by mentioning a few of the famous outstanding results, or the famous conjectures about prime numbers, as well as an important result or two. So the first thing I'm going to tell you about is, so this is a little bit descriptive. It's not as if there's loads of exercises attached to this. Well, when I show you the last result, the twin prime conjecture, we are going to prove something related to that, kind of a counterpoint or a companion result to the twin prime conjecture. So first of all, we'll introduce this function pi. Now this is one of the few places in mathematics you see pi being used for something other than the ratio of a circle's diameter to its circumference to its diameter. Okay, but this is not that use of pi. We're just using pi here because it's the Greek p sound, and this is the prime counting function. I've written there p r to r. That second r should be a z. Should be the integers. Should correct that to the integers. So it's a function that's defined on all real numbers, positive real numbers, you could say. I don't worry too much about that, but anyway, it's a very simple function, or in one way, a very simple function to define. It simply counts the number of prime numbers that there are less than x. Okay, so it just counts up the number of primes that there are less than x. So it's measuring the number of primes between 0 and x, or between 1 and x, or whatever. So this quantity, so this is telling you how many primes there are in a certain range. So mathematicians have long been interested in getting to grips with this function. I mean, if you graph it, you can draw a graph of the function. Computer. But I mean, there's no primes here. Then here's where you reach the first prime, and 3 is another prime, and 5 is a prime, 6 isn't, 7 is, 8 isn't, 9 isn't, 10 isn't, 11 is, 12 isn't, 13 is. So it's a staircase function. Sorry, I wandered down the thing. It should either be going horizontally across or up. Okay, it's counting the number of prime numbers less than x. So it's this flat line, and every time it encounters a prime number, it steps up 1. Okay, so 1, 2, 3. Counts the number of prime numbers. So the question is, well, if you graph it, and you can get the computer to graph it over large ranges, but how is it increasing? What kind of rate of increase does it have? So mathematicians have been interested in quantifying the size of pi of x for large x. So in the early days of number theory, Gauss and Legendre, by experimental work, just by studying, looking at all the known prime numbers, and seeing how many there were up to a certain point, they kind of formulated a rough conjecture that maybe pi of x increases like this function, x over log of x. So maybe x over log of x would be a nice approximation to pi of x. Okay? Now, x over log of x, as x is any real number, this obviously takes real values. But the idea is maybe it's an approximation to the value of pi of x. Okay? And it took until the mid-19th, just the end of the 19th century, before this was proved. And it was proved in this sense. So they have this rough idea that x over log x should be an approximation to pi of x. And the way it was proved is in this kind of statement, that if you divided pi of x by x over log x, divide pi of x by x over log x, or you multiply it by log x over x, in the limit, as x goes to infinity, this ratio approaches the value 1, and it converges to the value 1. Okay. So as x gets larger and larger, x over log of x becomes a better and better approximation, in this sense, to the value of pi of x. Now, the two values will never agree. Phi of x will never be the same as x over log x. But whatever the error there is between them, as x gets large, the error, relatively speaking, relative to the value of the pi of x, the error is converging to 0. Okay, so when you take the ratio of these two quantities, pi of x divided by x over log x, this approaches 1 as x goes to infinity. So this gives us a measure, as x gets large, of the density of the primes. Okay? The x divided by, if we're interested in the density of the primes, the prime density is often written as pi of x over x. That's the proportion of numbers that are prime up to x. Pi of x is counting the number of numbers that are prime up to x, and if you divide by x, then you get a proportion. Okay? And so this proportion, as x gets large, this proportion is approximately 1 over the logarithm of x. The error between those terms, relatively speaking, relative to what you're trying to estimate, that error is converging to 0. But that's this kind of adds to the infuriation because we know on average how many primes there are. Now, with the aid of this theorem, on average, there's approximately 1 over log of x primes up to the value x. We have a precise description of the average behavior, but we've no way of knowing when the next prime is going to come along, except for testing every number. Now, the way the prime number was proved is in an area of maths called analytic number theory, and a lot of this centers around the study of this famous function called the Riemann Zeta function. So the Riemann Zeta function is a function defined at a complex variable s. It's given by this infinite summation. So when s is equal to 1, it's the familiar summation, the sum of 1 over n, which is our harmonic series. One of the first things we studied in the Maths Fundamentals unit last year. But you allow a complex exponent on the value of n. And so this is studied in an analytic way. So the derivatives and integrals, the kind of complex derivatives and complex integrals of this function. When you study those, you can draw conclusions or make connections back to number theory properties of the prime numbers and the composite numbers and so on. And kind of using those ideas is how the prime number theorem was proved. And there's a famous outstanding conjecture called the Riemann hypothesis. Now this function, this zeta function has many zeros, many locations, many complex numbers s for which it takes the value 0. And there's a conjecture about these that these are all located along this line in the complex plane. So this is the line 1/2 plus I times b. So this is the line located at real part 1/2. So it's a line in the complex plane parallel to the imaginary axis at position 1/2 on the real axis. That's a conjecture that all the non-trivial, there are other zeros which are easily understood as the zeta function, but all the non-trivial zeros, the interesting zeros of the zeta function, are located along this line. Again, this is a conjecture. We don't have a proof of it yet. But there's lots of evidence being accumulated for it in the form of computer search. Okay, searching for zeros of the function and confirming that yes, they are lying on this line. And there's a lot of when famous conjectures like this develop and become well known, and people start to have a lot of faith in them, sometimes they get ahead of themselves and they build lots of mathematics assuming these conjectures are true. So there are certain branches, kind of speculative branches of number theory, and this occurs in other branches of mathematics as well, where people say, well, this conjecture's been around for a long time. We haven't found any contradictions to it or counterexamples to it in lots of computer search. So, why don't we kind of assume or pretend that it's true, and let's see what the consequences are. It's like exploratory mathematics, where it might all the results you reach might all collapse if somebody proves that this is false. But there's a kind of a general kind of feeling that this should be true. So let's continue on and see what mathematics we can build on. Okay. So there's a lot of conjectural exploration in mathematics that builds on some of these famous conjectures and works out the consequences of them, were they to be true. Is a Greek letter Zeta. It's a Greek letter Zeta. That would be equivalent to our Z, I imagine, yeah. But I'm not 100% sure. Yeah. But it's traditionally used for that function. Another famous conjecture that's around is the Goldbach Conjecture. That every even integer greater than 2 can be written as the sum of 2 primes. And you can do some pen and paper checking of this yourself. Whatever even number you test, you'll be able to write it as a sum of 2 prime numbers. Random even number off the top of my head.
Just proof that.
100. Oh my God, that's a bit big. Sorry?
No, say there's no proof.
There's no proof of this yet. It's been checked.
But can't you just do it for every?
No, you can't do it for every, because there's an infinite number of them. Yeah. Now people set the computer to searching and testing every even number, checking that it can be expressed as a sum of 2 prime numbers, and all the even numbers we've checked so far can be, or
What conjecture means, like a theory that has.
Yes, conjecture. Yeah, something which is perhaps got a chance of being true, and it's an interesting result, but it's something, and people are trying to prove it, but it hasn't been proved yet. So I mean, like 24. I was about to say that's 21 plus 3, but 21 is not prime, of course. 17 plus 7. 2 prime numbers to give you 24. Well, let's try 100. Somebody said 100. What are the 2 primes that give you 100? There you go. 1,000. You won't get that so fast. Okay. 59 and sorry. 59 and 41. Is that it?
Yeah.
59 and 41. Okay. But so computer search has failed. Computer search has failed to find a counterexample to this. So
Isn't that proof then?
it's not proof. It's evidence. Well, a proof is unarguable. I mean, I can say, well, who's to say that? So the computers, there's a highest even number that the computers have tested. Yeah, humongous, yeah.
Right.
But who's to say that the next even number they test will?
No, but computers are very sure that no one can do anything more than that. Because you're talking like so many figures, aren't you?
Yeah, but we're interested in truth. This is what the conjecture says. Every even number. Not just as many even integers as you can think of or you can test, but it's saying every even. There's an infinite number of those. So yeah, I mean, we've searched for counterexamples to it, these computers, but we haven't found any. We've tested a lot of integers, so there's a lot of faith in this, you could say. A lot of people have a hunch that it's true, but we don't have a proof of it. Now I'll just mention one more, and then we'll actually work through some arguments ourselves. I think I mentioned it before, but the twin primes conjecture. Every so often in the sequence of primes, you meet primes which are 2 apart. Actually, you meet them quite often. Oops, not 9. I said before that 9 was a prime number for some reason. We quite often meet primes that are 2 apart. We meet them a lot early on. And in the sequence of primes that we've investigated using a computer, it keeps on happening, even in the high up ranges. When you get to primes which are huge, of hundreds of digits, you still encounter primes which are 2 apart. 2 apart, so like there's just a difference of 2 between the 2 prime numbers. Yeah, and these are called twins. Twin primes, because they're close together. And this is another one of these famous conjectures, that there are an infinite number of these. Now we were able to prove fairly quickly that there's an infinite number of primes. But there doesn't seem to be any kind of simple argument like that, or any kind of, relatively straightforward argument like the one we saw for the infinite number of primes. I mean, maybe at first glance you think, oh, well, there must be a nice simple argument to prove there's an infinite number of pairs. But a lot of people have devoted a lot of time to this, and it seems to be a very hard thing to get a grip on. Now, there was a lot of progress made recently. Just 2 years ago, it's a Chinese mathematician working in America. I put a link to it here on the G+ page. Some of you may have seen it if you've been looking at the lecture recordings. But Yi-Tang Zhang is his name, and he was relatively unknown guy. He certainly wasn't a well-known number theorist. He wasn't, famous or anything. But he is famous now because he made the first real progress towards this problem. So the conjecture is that there's an infinite number of prime numbers which are separated by 2. Well, he proved in 2013 that there's an infinite number of pairs of primes, not necessarily twins, which are 2 apart. There's an infinite number of close neighboring primes, and there's an infinite number of them that are separated by no more than 70 million. So he proved this. Okay? He proved that infinitely often, as you go out to the integers, you'll encounter a prime. You'll encounter a prime p. That happens infinitely often. We've proved that. Well, he proved infinitely often you'll encounter a prime p, and somewhere within the interval from p to p plus 70 million, there will be at least one other prime q somewhere in that interval. Now the conjecture is that infinitely often you can find a p and a q that are just 2 apart. So he was the first one to make, at least get a first stab at the result.
Well, I don't get it. So saying the further there be apart is 70 million.
Yeah, that this happens infinitely often. Infinitely often you can find it just keeps happening in the sequence of integers.
So saying the further 2 prime numbers can be apart is 70 million.
No. It's not saying the furthest 2 primes can be a part of 70 million, because we'll soon prove that that's not true. It's saying infinitely often, so it keeps on occurring that you encounter a new prime, and somewhere within the next 70 million, you'll encounter another one.
That's not what I see. Like within, you're saying within 70 million you guarantee to find another prime number?
No, not that you guarantee, but just that it'll happen infinitely often. It's a bit hard to parse, or to infinitely often this happens.
So if you have a prime number within the number 70 million, you guarantee to get another prime number.
Yeah, but not for every prime number p. But it keeps happening. It keeps happening that along the way there'll be a prime number, and inside the next 70 million integers there'll be a second one. That happens infinitely often. The goal of it is to get to the twin prime conjecture, which says that infinitely often you find a prime p, and then the number 2 above it is also prime. So he made the progress that he reached this length of interval 70 million, whereas this is the goal, to reach an interval of 2. But this was a very significant step, even showing that you can get this close to the ultimate twin prime conjecture. And that initial work of his spurred on a lot of other mathematicians to improve his results and bring in other tools and combine it with his insights. And I think now they have it down to something of the order of 200, and the precise number will be in this article. I think it's 200 and something. 2010. It'll be somewhere near the end. It's something of the order of 200. Let's just say it's less than 300. So they've reduced this number 70 million down quite a bit on the way to 2. But they seem to be running out of ideas to get it down to 2. So maybe another new idea is needed as well.
Do you do Goldbach computers?
No, I don't think. I mean, I'm sure he used, but his proof was like a pencil proof. I'm sure he used computers to experiment and investigate, but it wasn't a computer search kind of result, I think. Yeah. Now, so that's just a small selection of some of the things about primes we don't know. And what I'd like to do in the rest of the time is prove a companion result to this. Okay. So the twin prime conjecture says that infinitely often you encounter twin pairs of primes that are just really close together. This is the closest together primes can be. And you can't have p and p plus 1 being primes, because p is a prime, p plus 1 will be an even number, so it'll be divisible by 2. So you can't have 2 primes right beside each other, except for 2 and 3 at the start. But this is the closest 2 large primes can be together, p and p plus 2. They can both be primes. The twin prime conjecture says that happens infinitely often. So we're going to prove something towards that. No, sorry, we're not. We're going to prove a companion result to that. We're going to prove so the twin prime conjecture says that infinitely often primes get as close as possible. We're going to prove now, and I'd like to lead you through a discussion of the result that there's arbitrarily large gaps between the primes. The twin prime conjecture says infinitely often the gap between primes is tiny. It's as small as it can be. It's just 2. Our result is going to be prove that there are arbitrarily large gaps between the primes.
What is arbitrarily?
So arbitrarily means it's arbitrary. I can find any size of gap somewhere between 2 prime numbers that I want. So it's arbitrary. There's no restriction on it. These gaps between the primes, a gap of any size between prime numbers, can be found between consecutive primes. Should say between consecutive primes. So let's say somebody asks for a gap of 1,000,000. We want to prove that somewhere in the sequence of prime numbers, somewhere along the sequence of prime numbers, you encounter a prime number, and then the next 1,000,000 numbers after it aren't prime. They're all composite. The next prime number after that one must come at least a distance 1,000,000 away from that one. And that gap is arbitrary. So whoever specifies the size of the gap, we want to prove that somewhere in the sequence of prime numbers, there's that size of gap between consecutive prime numbers. So that's the result in kind of English. So let's make it a bit more definite. Given any n, there exists a run of n consecutive integers all of which are composite. That's what we're actually going to. That's what we're actually going to prove. So given any n to be a positive integer, exists a run of n consecutive integers, each integer one after the other, all of them being a composite. So we're trying to find a location in the integers where there's no primes. And we want that location to be an interval of length n in the integers. Now this, when you first look at it, okay, it's a bit hard to see how to get going. And this could easily, it mightn't surprise you when you first see this. Maybe this could be an unproved conjecture. Maybe this is something that people have been trying to prove for years and haven't managed to. It has that kind of feel about it, maybe. But it is provable. We're going to prove it now. Again, it's just another example of sometimes easily stated facts about the prime numbers are extremely difficult to prove and haven't been proven yet. Twin prime conjecture, the Goldbach conjecture, every even number is a sum of two primes. And sometimes kind of similar looking or similar in feeling statements about primes. This is a statement about the absence of primes or the gaps between prime numbers. Sometimes these things are straightforward to prove. We'll be able to prove this now with just the concepts that we've developed so far. Now, it'll help us a bit if we talk about the location of this interval of n consecutive numbers. Suppose this run how do I phrase it? Oh, let's say consider a run of n consecutive numbers, n consecutive integers. Well, there's going to be a first one, which is going to have some value n. But then the next one is n plus 1, then n plus 2, n plus 3, n plus 4, I can keep going, n plus 5. And then it ends with n plus n. Sorry, this is n plus 1 consecutive integers. This is the 0th one, the 1th one, the 2nd one, the 3rd one. So there's actually n plus 1 consecutive integers. But that's not the point. What we're trying to prove is we're trying to come up with a recipe, some way of constructing where this run of consecutive integers is. We wanted some way of defining the start point such that all of these numbers are composite, such that none of them are prime numbers. So that's what the proof we're trying to prove. We're trying to prove that there's a gap of at least n somewhere in the integers between prime numbers. So we're constructing a way to say that there are no prime numbers in this list. And I think it's kind of surprising. In some ways, it's surprising that we can do that, or it's remarkable given that we don't have a good, thorough, clear understanding about the prime numbers anyway. It's an example of something we can't do. So we want to show, that this is a composite number. This is a composite number. Well, yeah, that's kind of a hint. Good observation. I didn't write composite under the first two. Being a bit vague about what happens at the sides, how could we show that all the numbers in the middle are composite? Well, how do we show a number is composite? There's only one way to show that a number is composite. Show that it's divisible by something. So for n plus 1, we want to show that n plus 1 is a product of two integers. We want to show n plus 2 is a product of two integers.
I thought you said m and m plus 1 are composite.
Oh, sorry, yeah, you're right. Yeah, so, yeah. So we want to factorize each one. Where are these factors going to come from? And I also like this result because it's extremely hard to see how to do it at the start. But then the answer is kind of staring you in the face in a way. Where are the factors of this n plus 2 going to come from? Where are the factors of n plus 3 going to come from? Where are the factors of n plus 4 going to come from? N plus 5. Really, some of the factors are staring us in the face, really.
You mean the one
No, just this page. They're actually sitting there in front of us. What kind of number could divide n plus 2? What kind of number could divide n plus 3? Was that a suggestion?
What's m represented?
Sorry?
What's m represented? Is there any number?
M is the location where this run of consecutive integers is. And we want it to have length n.
Okay.
Yeah? And we want all of them to be composite numbers.
Could you divide it by itself? No. Not by n, sorry.
Well, if this was divisible by n, then n would have to divide 2, and n would have to divide 3, and so on. No, that couldn't. But you did mention itself, and that's kind of a relevant thing. I mean,
That's the one before.
yeah. When you look at each number, there's a kind of a candidate sitting there for a factor of it. You've got n plus 2, and the only thing special about n plus 2 is that it's 2 clicks on from n. You've got n plus 3. The only thing special about n plus 3 is that it's 3 clicks on from n. 4. So maybe we can factorize this as something times 2. And n plus 3 is something times 3. And n plus 4 is something times 4.
Well, that depends on n.
Exactly. It does indeed depend what n is. Is there any kind of special n such that n plus 2 is divisible by 2? N plus 3 is divisible by 3.
But n would have to be even.
Yeah, n would have to be even. If it's
M would have to be like more called.
so we're looking for a number n.
What kind of m does this?
Yeah. What kind of a number n is this property that n plus 2 is divisible by 2, n plus 3 is divisible by 3, n plus 4 is divisible by 4? No.
Yeah, 0.
Yeah, but then some of these will be prime numbers then. 5 will be a 0, 5 would be a prime number, 3 would be a prime number. We're trying to find composite numbers. You see, 2 divides 2, and 3 divides 3, and so on. So, like, the only way 2 can divide m plus 2 is if 2 divides m itself. We said before, n has to be even. The only way that 3 can divide m plus 3 is if 3 divides m. The only way 4 can divide m plus 4 is if 4 divides m. It's already divisible into that way. So we need to have that 2 divides m, 3 divides m, 4 divides m, 5 divides m, etc. If any number, what kind of number m has that property? That it's divisible by everything. It's divisible by a range of consecutive integers. Factorial, yeah. Let's just define n to be a factorial. Then it'll be divisible by 2, 3, 4, 5, up to some point.
So n factorial.
Then it has loads of factorial. Well, n factorial, you see, you called me up about, why didn't I talk about m and m plus 1? The only one I'm sure will be composite is this one, m plus 2. See, I know m, if I define m as n factorial, m will certainly be a composite number. Well, I don't know about n plus 1. Maybe that will be a prime number, maybe that will be a composite, I don't know. I can't say that one, well, I can say that 1 divides it, but that doesn't mean it's a composite number. To prove it's composite, you have to show a genuine factorization. But if m is n factorial, then certainly m plus 2 is composite. And this one's composite. This one's composite. This one's composite. So the run of composite numbers begins here at m plus 2. M plus 2 is the first one. So if we want there to be n composite numbers in this list, we'll have to go all the way up. Because we're beginning at 2, we'll have to go up to n plus 1. We'll have to take n plus 1 factorial. So it's just this observation. If n was a factorial, it would work. Just as a kind of rough observation. Because factorials have this property. Factorials are divided by each number one after the other. So we just have to make it a big enough factorial. So if we want n consecutive composites, so this is a location on the set of integers where there's no prime numbers, and we can make this as large as we want. So if we want n consecutive composites, we can find them at, well, if we let m be n plus 1 factorial, then each of these numbers all the way up as far as m plus n, and then m plus n plus 1, all of those numbers will be composite. And there's n of these numbers in the list. Okay, so 1, 2, 3, as far as n. N of those numbers. So that means somewhere in the list of prime numbers, the gap between consecutive prime numbers is at least a million. At least a million. At least a million. Million.
Where does that mean?
Well, it's a large number off the top of my head, because we could set n to be a million. If we set n to be a million, then this list of integers are all composite. So whatever the last prime before this run of integers was, none of these are primes, and then whatever the next prime is, the gap between those two consecutive primes is at least a million.
Oh, that's too random.
That's just a big number off the top of my head. But the point is, it can be any number. It can be a billion. You can make n anything. The same construction works. So somewhere in the list of prime numbers, the gap between consecutive prime numbers is at least a billion. Okay. Because here's the location where you've got a billion consecutive composite numbers.
You can't say at least, because you said it also works for a billion.
Yeah, but I'm just saying somewhere the gap. Not that the gap everywhere is a million, But just that somewhere there's a pair of neighboring prime numbers, but the gap between them is at least a million. Because there's a run of 1,000,000 consecutive composites. So this shows that arbitrarily large gaps can be found between consecutive prime numbers. Okay, because arbitrarily large runs of consecutive composite numbers can be found. And that stands in contrast, or it's kind of like a companion result, or a result in the different direction to the twin prime conjecture. The twin prime conjecture says infinitely often the primes are as close as they can be. Just P, and the next one, 2 on, is a prime. That's conjecture. But in contrast, we know, even though they may infinitely often get as close as possible to each other, they also, consecutive primes, get arbitrarily far apart as well. Okay? This construction shows that if you want a gap of any size, somewhere there's a prime number, and the next prime number, the gap between them is as large as you want. So this stands in. This stands in contrast to the twin prime conjecture. Okay, so it's an odd week, so I see you again, don't I, on Friday? Yes, so in the second lecture, I think we'll finish off some of the exercises at the end of this chapter, and maybe look ahead to chapter 4 as well. Okay, thank you.